Suppose we have a randomized double-blind placebo-controlled clinical trial with 3 treatments: drug, dose 1, drug, dose 2, and placebo. And let's say we have an outcome variable of improved yes, no. The data could easily look something like this. So, on a typical final exam question, it might ask us to perform a chi-square test of independence. I'll write this down. Perform a chi-square test of independence to test whether treatment and improvement are independent. Now, since this is a randomized, double-blind, placebo-controlled clinical trial, and since these 3 levels of treatment have been randomly assigned to all the subjects, we can actually test for a causal relationship in this case. But your final exam question may not go into that level of detail. It probably will ask you to state the null hypothesis and the alternative hypothesis. And so I will do that for you. So the null hypothesis in a chi-square test of independence is always that the attributes are independent. So we'll write something like treatment and improvement are independent. And the alternative hypothesis for a chi-square test of independence is always that the 2 attributes are dependent. Now, your instructor has to give you a significance level for performing this hypothesis test. And if no significance level is given, the default significance level is alpha equals 5%. So I'm going to write alpha equals 5%, but your instructor may give you a different alpha level, though this is the default in the real world. And so we need to apply Pearson's procedure. Now, I'm going to show you exactly how to do this step by step, but I'm not going to explain why the expected frequencies are what they are. I'll just show you how to get them. So these are called observed frequencies. And sometimes what you might be asked to do, which in the real world you would have to do, is you'd have to have a label for this table. So it might say something like observed, and then in parentheses, you'll put the word expected. Frequency. Of improvement. Now, if you really want to get good credit and impress your professor, it'll say something like this: cross-classified by treatment. Now, this is a full credit label here. So, and I want to call your attention to something. So when we say observed, and then we put expected in parentheses, in standard written English, the reader would think the observed and expected frequencies were the same. But in stats, this means something very different. It means that in parentheses, we are going to put expected frequencies under the observed frequencies, just like this. So, and I'm going to show you, of course, I'm going to show you how to calculate these expected frequencies. But this is what the table would look like. So when you read a table that says observed parenthesis expected frequency, that means the numbers that are in parentheses are the expected frequencies, and the numbers that are not in parentheses are the observed frequencies. And this is a pretty standard way to make a table in statistics. And if you label it this way on your final exam, and you know, your instructor is the kind of instructor that wants to see your work and doesn't give multiple choice questions and really wants to see how you do everything. If you were to label the table this way, you know, you'd have to impress your professor a little bit. So this really is your step one over here, is to just set this whole thing up like this. A nice setup with a nice label, making sure you make room in your cross-classification frequency table. That's what this thing is called, for your expected frequencies. So that's your step one. Now, step two are these hypotheses over here. So I'm just going to write step two. And the next step is to calculate your expected frequencies. And this is really, really easy as long as you know the rule. So I am going to write over here, step 3. Expected frequencies. And there's a little formula for that. The expected frequencies, I'll call them E, is equal to the row total times the column total over the grand total. And you'll have to memorize this formula here. And now I'm going to show you how to apply this little formula. So I want you to notice we have these row totals, row total, row total, row total. And then we have a column total here, column total here. And this is called the grand total. So maybe I'll write this. And this is the first row total, second row total, third row total. First column total, second column total, grand total. So I want to show you how to apply this formula here. So the row total times column total over grand total, that's your expected frequency. So what I want to do is I want to show you how to get this expected frequency here. So I'm going to do it in this color, just to show you. So the expected frequency in this row and this column, see, I want you to notice that this is the first row and this is the first column. So the row total here would be 46. The column total in this column is 22. And the grand total is 139. Row total times column total over grand total. Row total times column total over grand total. So let's grab our calculator and actually put that in. I want to make sure this is in the frame. All right. So we're going to take 46 times 22 divided by 139, and we're going to get 7.2806. So let's put that in. 7.28. And I'm only going to round it to the nearest thousandth. So if you see it's 7.28, this 0, I'm going to round up to a 1 because this is a 5. So we'll do it to the nearest thousandth. That's good enough. Now, I want to show you something very interesting, right? If this is your expected frequency in this first row, and we know that it has to add up to 46, we can get this second one just by subtraction. So if we take 46 and we subtract 7.281, we get 38.719. Just by subtraction. Okay, so let's do another one. I think I'm picking this completely arbitrarily, but I think I'm going to do this one here, and I'm going to do it in red. So, and I picked this completely arbitrarily, but you'll see something interesting after this. So, our row total, this is in the second row, so our row total is 44. Our column total in this column is 117. And our grand total is 139. So let's actually do it so we can get this expected frequency, and I should put a little arrow over here to show you where this came from. All right, so let's do this. So let's go, make sure I'm in the frame. 44 times 117 divided by 139 equals, we get 37.036. 37.036. Now, here's something that's really interesting. I picked these two arbitrarily. Now I got this from simple subtraction. Notice I can get this expected frequency from simple subtraction. I can get this one from simple subtraction. Really, we don't even have to use the formula anymore, because if we take 44 and we subtract 30, well, let me make sure I'm in the frame. So let's take our 44 and subtract 37.036. What do we get? We get 6.964. Let's put this in. 6.964. Now, if you notice, we can get everything else by simple subtraction. See, this plus whatever this is has to add up to 22. So we can get this quantity just by taking 22. Let me make sure I'm in the frame. Yes, I am. So let's take 22 and let's subtract 6.964. And then let's also subtract 7.281. Let's see what's left over. We have 7.755. And we can do the same exact thing here, because this plus whatever this thing is has to add up to 117. So by simple subtraction, or we could actually do an easier one. We could do it that way, or we could take 49 minus this to get this. That's a little easier. I think I'm going to do it that way. Why do something difficult when you could do the easy way? So let's take 49 and subtract 7.755, and we get 41.245. And I want to call your attention to this idea. You probably heard your professor speak of this. But you may not necessarily have seen it quite in this way. What you may have noticed was I only needed to use this expected frequency formula for 2 of the values in this table. You see, every other value, once I got these 2, I was able to get by simple subtraction without having to worry about applying this formula. So 2 expected frequencies were required given these row totals, which are sometimes called row marginals, and these column totals, which are sometimes called column marginals. So we were able to get this just by simple subtraction. We only needed 2 of these expected frequencies. And that's why your professor mentioned this term degrees of freedom. So under the null hypothesis, the chi-square score in this particular situation has 2 degrees of freedom. And we say df equals 2 as a simple way to say it has 2 degrees of freedom. Now, some professors prefer you to calculate all these expected frequencies using this formula because they want you to get practice using this formula, and they consider, you know, doing the simple subtraction. You know, I don't know if cheating is the right word, but some professors don't even tell you that you only need to use the formula twice when you have a 3x2 table. Now, if you had a bigger table, you'd have to use more of them. But under the null hypothesis, there are 2 degrees of freedom. And there's actually a formula for the degrees of freedom, which your professor may have told you, and I want to tell you what that is. So if we let R equal the number of row categories, and we let C equal the number of column categories, then the degrees of freedom of the chi-square score that we are going to calculate under the null hypothesis is equal to the number of row categories minus 1 times the number of column categories minus 1. So in this case, there are 3 row categories: the drug at dose 1, the drug at dose 2, and the placebo. So in our case, this is equal to 3 minus 1 times, now there are 2 column categories. There's improvement yes, there's improvement no. So that's 2 minus 1. And of course, 3 minus 1 is equal to 2. And 2 minus 1 is equal to 1. So there are 2 degrees of freedom by the formula, just as we saw that there were 2 degrees of freedom simply because you only needed to put in 2 expected frequencies, and you could get the rest by simple subtraction. That's why this formula works the way it does. So it's not super hard, even if you forget the formula for degrees of freedom, which some students do, to see how many expected frequencies you need to fill up your table, knowing that you can get the rest of the frequencies by simple subtraction. So that's the degrees of freedom, and these are the expected frequencies. So if you look at this carefully, before I actually show you how to get the chi-square score from the actual test, let's just take a look at this table a little bit and see if we can figure out an idea of what's going on. So the observed frequencies are these numbers here, and the expected frequencies are in the parentheses. So now I'm going to put this table into the frame a little bit more so we can see this carefully. Move it down. And let me show you what this is saying. This is saying we observed 9 study participants who improved and were given the drug at dose 1. But we would only expect about 7.281 people to fall into this category under the null hypothesis. Now, what does the null hypothesis say? The null hypothesis says when treatment and improvement are independent. So this is what this table is saying. If the treatment and improvement are independent, then we would expect about 7.3 people to fall into this category. But we got 9. That's more. More yeses in this category. That could look pretty good, possibly. So now let's look at the drug at the second dose. So here, we would expect about 6.964, which really is almost 7 people. We would expect about 7 people at this dose with the drug to improve. But we only got 6. So it's looking like maybe this dose might be not as good as this dose. Usually the second dose, when you make a table like this, dose 1 is lower than dose 2. That's typically the way you'd present it. You usually present it in a table with increasing dose. So the higher dose may not actually be as good as the lower dose, and that can totally happen. You can get toxicity at a higher dose. Let's look at the placebo. So here, with the placebo, you would expect 7.755 people to improve and be given the placebo. That's what we would expect by chance. And by chance, I mean assuming treatment and improvement are independent. But we only got 7. So we would expect a little more improvement in the placebo, yes, than we actually got. So it's looking like this drug at dose 1 may possibly be a good thing. But here's the next question. Is it statistically significant? So what the chi-square test of independence allows us to do, it allows us to pool all this data and do one hypothesis test to see if there's any connection. I'll use the term connection. Any connection, any link. In this case, it's a causal relationship because of the randomization between treatment and improvement. And because we're looking at all these treatment levels with improvement at the same time, this is sometimes called an omnibus test. And that's a great, if you could throw this on your paper when you're writing up your final exam, if you don't have, a teacher who gives multiple choice, it's a pretty impressive thing that you know that. Omnibus meaning you have all these things. You're not just comparing, say one drug with a placebo. We're actually comparing 2 doses and a placebo in the same statistical analysis. And that's one of the things that makes chi-square such a useful test. But it's only a good test to start with. It's not the end of it. But it could be the end of it if you have a non-significant result. So step 4 is called a contribution table. And the reason it's called a contribution table is because we're looking at the contributions to the chi-square score. So what we're going to do is we're going to make a little column for the observed frequencies, for the expected frequencies, and then we have this interesting little metric, observed minus expected squared over expected. And this little metric comes from this guy in the late 1800s to the early 1900s named Carl Pearson. And Carl Pearson showed back then that the null distribution is a chi-square, and I'll show you what that is a chi-square random variable. And he showed that these are the degrees of freedom, that it depends on the number of rows and the number of columns. And this is the degrees of freedom of the null distribution. So he showed that over a century ago. So all we're going to do now is we're going to copy these in. So here we have 9 is the observed, and the expected is 7.281. And this one's done, so now we have 37 is the observed. And the expected is 38.719. First row is done. And now 6 is the observed frequency. I'm going to put a little line just to organize my work. And 6.964 is the expected frequency. And 38 is the observed frequency. And then 37.036 is the expected frequency. All right, 2/3 done. And now 7 is the observed frequency. And 7.755 is the oh, I put it in the wrong place. 7.755 is the expected frequency. And 42 is the observed frequency. And 41.245 is the expected frequency. Okay, so now the next step in this contribution table is to grab your calculator, and I'm going to show you exactly what buttons to press. What we want to do is we want to take the 9, so we want to take the observed, subtract the expected, square it, and divide by the expected. So I'm going to do it exactly as the formula is written. First thing I'm going to do is hit the parenthesis button, which is this button right here. And then I'm going to go 9 minus 7.281. And then I'm going to close the parenthesis, and then I'm going to hit the x squared button right here. And then I'm going to hit the divided by button, and then 7.281 equals, and here you see we get 0.40, I'm going to round this 5 off to a 6, 0.406. Now I'm going to do the next one. And I should tell you, these are called contributions. Because each one of these values contributes to the total chi-square score, which is the thing that we're going to talk about next. All right, so let's do the next one. Make sure the calculator is in the frame. Yeah. All right. So we're going to hit the parenthesis key, 37 minus 38.719, close parenthesis, divided by 38.719 equals, and we get 0. Oh, I didn't square it. I made a mistake. I noticed that. Let's do it again. So we have 37 minus 38.719, close parenthesis, squared, divided by 38.719 equals, and we get 0.076. 0.076. All right. 1/3 done. All right, let's do the next one. So here we have, let me make sure this is in the frame. So here we have 6 minus 6.964 closed squared divided by 6.964 equals, and we get 0.133. And then, let's do the next one. We have 38 minus 37.036 closed squared divided by 37.036 equals, and we get 0.025. All right, 2/3 done. Let's continue. So close parenthesis, 7 minus 7.755, close parenthesis, squared, divided by 7.755 equals, and here we have 0.07. I'm going to round this 3 up to a 4. 0.074. The last contribution. Here we go. So we have parenthesis 42 minus 41.245, close parenthesis, squared, divided by 41.245 equals, and we get 0.014. 0.014. I'll round this 3 up to a 4. 0.014. So these are all the contributions to this chi-square. So now the next thing we're going to do is we're going to add them all up, and we're going to get a chi-square score. And we showed that the degrees of freedom was 2. We put the degrees of freedom as a subscript in this symbol here. So this is the degrees of freedom. And now we add all these up. And this gives us our chi-square score. So let's do this. So we have .406 plus 0.076 plus 0.133 plus 0.025 plus 0.074 plus 0.014 equals, and we get 0.728. So this is called our observed chi-square score. And this is the symbol for our observed chi-square score. So this part over here, this is the Greek letter chi, and this part here is chi-square. That's what this symbol means here. And this subscript, too, is the degrees of freedom. So this is how, If it's in a multiple choice question, your professor will, put a bunch of symbols and ask you what's the appropriate symbol. And if it's a free response question like what I'm doing, where your professor may want to see you actually do this whole thing from start to finish, this is the most ideal way to represent the observed chi-square score. So that's step 4, but we're not done yet. The next thing we have is step 5. So in step 5, what we have to do is we have to interpret this chi-square score. And for that, you need a decision rule. And we have this thing called a critical value. And the critical value is just a fancy term for a percentile. Of the chi-square distribution. So let me show you how to figure out what this critical value is. And it's easiest to do it by example. So if alpha is equal to 5%, which means we're performing the test at the 5% significance level, then the critical value, I'll just write crit for critical value. The critical value is the 95th percentile. And if alpha is equal to 1%, another common significance level in the real world, then the critical value is equal to the 99th percentile. So I hope you see the pattern here, because 5 plus 95 equals 100. 1 plus 99 equals 100. And if your professor was to ask you to do this at, let's say, suppose your professor asked you to do this at alpha equals 2%, the 2% significance level. Can you figure out what the critical value that you would use would be? Well, if you said the 98th percentile, you'd be right. So this is all there is to the critical value. It's really not the hardest thing in the world. Let me give you the actual decision rule. So here's how you use the critical value. So if the observed value of the chi-square score is greater than or equal to the critical value, then we reject. I'll just write REJ for reject, the null hypothesis. Otherwise, we fail to reject. I'll write FTR for fail to reject, the null hypothesis. So this is the decision rule. So let's actually do it. This video is step by step, doing everything. So what we're going to do is we're going to make a little table. We're going to have the chi-square score, and we're going to have the crit. And since in the very beginning, we agreed that we would do this at the 5% significance level, the critical value in our case has to be the 95th percentile. So what I'm going to do is I'm going to grab my statistics book and I'm going to look this up for you. My statistics book, I'm going to go to the very back of the book And you're probably not using the same book, but you're going to have something similar here. See over here in Appendix A, it says selected percentiles of the chi-square distribution. And we're going to go to 2 degrees of freedom. And we're going to go to the 95th percentile, which is right here. And we see the 95th percentile is 5.9915. So I'm going to write that down. 5.9915. And the chi-square score that we calculated was 0.728. So we have a nice little table with our observed chi-square score and our critical value. And now, all we need to do is apply the decision rule, which is right here. It says, if the chi-square score is greater than or equal to the critical value, then reject the null. Otherwise, fail to reject the null. So here you see we have a chi-square score that is not greater than or equal to the critical value. So since our observed chi-square score is not greater than or equal to the critical value, we fail to reject the null hypothesis. And this is the answer in statistical lingo, just this. This is the answer in stats lingo, fail to reject the null hypothesis. And really, you could just write FTR space H sub 0, and that's your answer in stats lingo. But dollars to donuts, your professor wants you to express the answer in the original context of the problem. And the original context of the problem deals with a relationship between treatment and improvement. Is there a significant relationship between treatment and improvement? And in this case, we can actually test for causality because of the randomization. So is there a significant effect of treatment on improvement? The answer is no, because we failed to reject the null hypothesis. So the way you would write this is there is no significant treatment effect on improvement at the 5% significance level. This is your full credit answer in the original context of the problem. There is no significant treatment effect on improvement at the 5% significance level. So when we looked at that, in the beginning we were thinking, well, we got more patients who improved on dose 1 of the drug than we would expect if they were independent. We got more mathematically, yes, but it wasn't statistically significant.